Hello and welcome to our Wednesday webinar from the IEA Clean Coal Centre. My name is Rebecca Cameron and I am the events officer here. Our monthly webinars are based on our technical reports which are available from our website www.iea-coal.org. Residents of member countries and employees of sponsor organisations can download our reports at no charge after a one-off registration. The subject for today's webinar is Beneficial Uses of Fly Ash, presented by Dr. Ian Reid. The report for this topic will be published by the end of March.
Right. Thank you, Rebecca. We've carried out a set of studies recently on direct products from coal and coal wastes, including carbon products and even carbon dioxide. But today's webinar is on coal fly ash. Yeah, just to introduce myself, I'm Ian Reid, one of the studies authors at the Centre, and are some bioinformation on the slide. This webinar gives a brief review of the findings from our new report on fly ash, and that'll be available on the website soon. Coal fly ash is a combustion waste. It has been controversial due to issues on storage, and it is much preferable to use it in products. In fact, there's a change in progress where instead of looking for ways just to avoid storing fly ash, as in the past, there's now a rising demand for fly ash as it has beneficial properties, and I'll outline some of those today. The reduction in coal power generation in some countries means that there's a shortage of fly ash, and it is now need to import it. So the market for ashes is changing, and it is gradually becoming a commodity material. In today's webinar, we'll briefly consider the nature of fly ash and how it is obtained before progressing to uses, just for those that aren't as close to the industry. And of course, the most important use of ash is in construction, where not only does fly ash augment properties of materials, but has an important role in reducing the environmental impact of construction. So I'm going to spend a little time on that. But there are a number of alternative uses, including recovering metals, replacing the mining of mineral ores, the preparation of catalysts, most importantly zeolites, that are also used in water purification, and advanced composite materials, a very exciting area, and also agricultural applications. Before looking at how we use fly ash, this diagram shows the collection of combustion waste products in a modern coal power station. The ash is the mineral matter originally present in coal, so in general amounts to about 1/8 of the coal fed to the plant. So we're creating a lot of ash in a 1 megawatt plant. 1 gigawatt plant. And each ash particle is derived from combusted coal that has passed through the hot zone, partially melting ash, forming glassy spheres. Bottom ash is shown here, and it's collected directly off the combustor. It's a granular material, but it's of the same composition. The fly ash is collected after the heat recovery, after removing NOx, treating for mercury, and it's then collected in an ESP or bag filtration system. The reason it's collected, of course, is to reduce small particulate emission from the plant, which could damage your health. It's the dry fly ash that's the focus of today's webinar, but there is also conditioned ash that's collected for storage, so water is added to the ash. And for completeness, the other product that's obtained from these plants is gypsum from the flue gas desulfurization unit. Right. The amount of the amount of fly ash incorporated into construction is increasing as structures become stronger and more water repellent. This picture shows the new sea bridge between Hong Kong and Macau, where testing showed the optimum cement mixture to be 25% of fly ash, same with bottom ash, and the remainder Portland cement. So only half of the cement is manufactured. The properties of the cement are especially important for the tunnel section. There's an abundance of fly ash available, but not always where it is needed and of the required specification. Stored conditioned ash has to be upgraded before it can be used in most applications. The demand for all construction materials is rising, and that is true for fly ash. And that means it now has a value that's rising, but about 1/3 of cement at the moment. And cement makes up about 1/7 of concrete. The modern use of fly ash really began in Germany in the 30s, but the history of its use in construction is much older and dates from the Romans' use of volcanic ash. And the picture shows the beautiful concrete ceiling of the Pantheon in Rome. The previous wooden structures had burned down. The reason this structure has survived is because of the interactions of ash with the mortar that has prevented microcrack formation. Fly ash is very similar to volcanic ash in its composition as an aluminosilicate material. And the properties and durability of this material are evident, and that's why the use is increasing. In the USA, about half of the fly ash was used, but that has now reached 64% and rising. For China, in high population regions, the use is 100%, and ash is imported from remote areas. The increased demand amid higher usage and falling coal generation in Western nations has resulted in an export trade. If we'll turn to some of the environmental aspects, this picture is of Sao Paulo in Brazil, the 12th largest city, where the population has increased by a factor of 10 since the 1950s. I've chosen that city because it was highlighted in a recent conference in Miami, where there's growing concern over the availability of construction materials. These are directly linked to population growth, and the manufacture of cement now exceeds 3 billion tons, and this makes the production of cement the largest industrial greenhouse gas emitter. If you substitute 20% of Portland cement by fly ash, that has a profound effect on the energy use and greenhouse gas emissions of construction. It's one of the few ways of reducing the environmental impact, and of course also means less mining. And with enhanced properties, if structures such as bridges last longer, there's a major gain. The reputation of fly ash as a useful material suffered due to issues around storing conditioned ash. There are high-profile cases where the containment has failed, contaminating river systems. And as ash can contain heavy metals, then these have leached out polluting streams. In bricks and concrete, tests confirm that heavy metals are trapped inside the structure. They're encapsulated inside the inorganic matrix. And indeed, a novel storage option that's being explored now is dry compaction of ash. The presence of some residual carbon reduces the emission of mercury compared to bricks with no ash. All right, and now turning to some of the ash properties. This micrograph shows the perfectly round spheres of fly ash. Most are solid, but some shown here are hollow, and these are termed senospheres. These are highly valued products and are incorporated into filler as fillers. Some ash particles are agglomerated and become more like bottom ash. The specification for ash has evolved for each country independently, but is of more significance now that ash export is underway. The key factors are the carbon content, where too much impairs the strength in concrete, the particle size, which can fill interstitial spaces, calcium levels, where high calcium means less lime use in cement mortars, and contaminants. The contaminants are not always specified, but the famous one is radioactive ash from a specific mine in China, which can be used in construction. Ash beneficiation processes are coming on stream, as some ash deposits must be removed, and these can then be manufactured to exact compositions. So why is ash useful in construction? We've already seen the effect of volcanic ash in the durability of an ancient structure. The improved strength partially comes from the way heat is released. In the hydration of Portland cement, the temperature can rise too quickly, and if a maximum is breached, then microcracks form, weakening the structure. The fly ash reaction is slower, and that reduces the peak temperatures. Also, at least the full strength of the material is achieved and usually exceeded after several months of setting, in the case of large concrete structures. I won't go into the chemistry here, but there are more details in the report for those that are interested. The benefit of fly ash is especially seen when forming these large continuously poured concrete structures, such as for dams and foundations of buildings. India is trying to change the brick industry away from clay bricks to fly ash ones, as there are currently 100,000 clay kilns that are all fired 24 hours a day and require raw clay obtained from arable soils, amounting around 5,000 acres each year. The switched ash bricks would substantially lower the environmental impact and provide a more reproducible brick that doesn't need to be fired and has more strength. Now, construction is by far the most important use of fly ash and covers buildings, dams, bridges, embankments, bricks, and so on. And it is of growing importance to that sector. However, I would like to look at some of the other uses of fly ash. Looking at commodity metals from ash, there are three that can be attained from fly ash that are important at the moment. The recovery of aluminium competes with mining for bauxite and processing by the Hall-Héroult process that electrolyzes ore. Some fly ash in China is especially high in aluminium, which is recovered chemically and provides about 20% of overall aluminium demand, so around 10 million tons. Fly ash is one of two sources of germanium, which is important in the manufacture of transistors, and a new process is under development in Australia to recover magnesium from lignite, which is useful in lightweight structures. So there are a number of initiatives on commodity metals. But perhaps the more exciting area at the moment is in the recovery of rare earth elements. These are mainly found in the lanthanide series of the periodic table, which I've shown here, together with scandium and yttrium. Demand for these is rising rapidly, as they're needed in all modern electronic gadgets, but also for electric motors. So the transition to electric vehicles will need around 30 kilograms for each electric drive. And a 5-megawatt wind turbine needs about a ton of neodymium. And perhaps and terbium is often added, which is much more expensive, to control the change in magnetic properties with temperature. There is a shortage of supply. Apple recently announced they would recycle all iPhones to recover lithium and these elements. And waste electronic recycling is really getting underway. I think neodymium prices has doubled in the last few years. China has near monopoly over mined RE and smelting, and that has alarmed other countries where there is such a dependence. There's a history of extracting metals from coal, but these are normally present at much lower levels, typically around 35 ppm. But some coals contain about 10 times that level. And the interest in fly ash is that once combusted, that rises again by a factor of 8. So you can approach around 0.18% of RE. The issue for processing the ash is that the RE are largely trapped inside the structure, and so the severity of the chemical extraction has to be greater than for raw coal samples. The options for improving the extraction are under urgent investigation now. For example, they found that small particles have a higher proportion of REE. So physical separations are being conducted, and also sonic treatment to open the structure. Expect pilot plants to be operational soon to test these extraction methods and the economics, and of course meet 21st century standards for environmental processing. Fly ash has an important application in advanced materials, and I've got a few examples here. One of the properties that makes fly ash a useful constituent when pouring concrete is that the small glassy spheres act as a lubricant, aiding the pouring of concrete. And that property is finding out direct use for fly ash as a proppant in shale gas recovery. The small spheres can penetrate cracks more easily, and their high compressive strength then keeps the cracks open, allowing gas to escape. And this is already in use in projects in China. There are two examples. The other two examples are concerned with the application of carbon fiber and graphene. Carbon materials are becoming more significant, and when combined with fly ash cement, offer a new higher level of bonding. And there's a considerable interest in this, as it reflects the Pantheon concrete durability. Carbon fiber could replace steel in reinforced concrete, and that offers a material that is then corrosion resistant, with implications for the lifespan of essential infrastructure. Graphene operates at a smaller scale and has really been a research material until recently, but is now after a period of frenzy in patenting applications, is now realizing commercial products. It acts at a small scale to prevent crack propagation. So graphene actually can bridge micro cracks in a structure, preventing them from expanding. And one of the more recent applications for graphene is in a material for mending potholes in roads, which is a bit of a plague around the world. There are also composite materials where fly ash can replace up to 30% of aluminium, for example, to form a cheaper but more importantly a lightweight composite panel. And these are materials used to protect armored vehicles. Turning now to ash and catalysis, the researchers are exploring use of fly ash directly as catalyst supports in a wide range of applications, some related to hydrogen production and carbon capture. But as an alumina silicate material, the ash is already close to the composition of zeolites. These form about half of all catalysts and are an important potential application of fly ash. The alumina content tends to be a little low, so the main processing step to convert it to zeolite is alkaline fusion to remove some silica, and that's then followed by polymerization and crystallization of the zeolite. The picture on the left shows an idealized classic cage structure that gives zeolite extremely high surface area that can trap contaminants, and this surface is treated to change its properties, so to attract different components from a contaminated solution. on the right, the micrograph shows the crystals formed from fly ash. These are particularly well formed. Normally, they might not look as nice as this, but tests have shown them to perform as well as zeolites prepared in the normal way from diatomaceous earth. Research initiatives are looking at contaminant removal and replacing conventional zeolites, but also there may be an application in pressure swing carbon dioxide absorption for carbon capture. Really looking for cheap materials to lower the cost. The issues for successful deployment for fly ash as zeolites is the cost of the fusion step and the rising value of fly ash, where we think it's rising about 8% per annum, slightly faster than cement. Turning to fly ash in agriculture, there's a considerable history of fly ash use in agriculture, especially for high calcium fly ash used to adjust acidity, and conditioned fly ash can be used for this purpose. But fly ash can offer other benefits that can help to address the deterioration of soils. This is of increasing concern and is subject of a number of UN initiatives where the fertility and fertility loss of soils is a concern, but also desertification is a concern. Fly ash can improve the texture, improve the soil in a number of ways. The texture improves, it's increased aeration and percolation, and improves water retention, especially important in regions affected by drought, as well as addressing sodicity and acidity. There have been recent trials with volcanic ash to demonstrate enhanced carbon retention in the soil, a factor that has been falling in recent years and is of major concern for climate change. And if successful, the plan for that program is to introduce fly ash and test it for that application. The main concern, though, is that there are a number of toxic elements in fly ash, mercury and arsenic among them. If in moderate or low levels, these are easily accommodated, but some fly ash is inappropriate. Some guidelines suggest intervals between applications should be several years, and the loading rate should be modest. But this would ideally be supported by chemical analysis to confirm the safe use of ash in this application. Right. Just to reflect on today's webinar, then, as we're coming to the end, the most important use for fly ash is in construction by far. The proportion of fly ash in cement is rising. It typically was 10%. Now we're seeing 25% and more. Some buildings using 50% fly ash. And that's not just to find a use for a waste material, as perhaps in the early days, but the material is superior. The environmental benefits are clear. Avoid mining fresh materials, avoid high temperature processing in cement kilns, make more durable structures that have a longer useful life, all combining to lower the carbon footprint of construction. We're currently making the equivalent of Paris each month, and that is set to increase with the population. So fly ash can make a very significant contribution to the carbon footprint of construction, and perhaps is one of the few ways to do so. There's already commercial extraction of aluminium and germanium from fly ash, and magnesium should be added to that list soon. The high-profile sector just now is to obtain rare earth elements from fly ash and derived from coal that is already enriched in these essential elements. Trials are underway. The technology has been demonstrated, and it's now down to economics on how significant this technology will be. There's a new initiative to combine construction materials augmented by fly ash and then strengthened further with carbon fiber or graphene It's a very exciting area that's adding a new level of bonding into concrete and cement materials. As the cost of graphene and carbon fiber falls, it's expected to be the case that even stronger, longer lasting materials can be made. The application of ash can provide substantial benefits to agriculture, and there's interest in carbon retention from fly ash added to the soils. But the caution is that the concentration of certain elements must be within acceptable limits, avoiding toxicity of the soil and the food grown from it. Finally, the composition of fly ash is quite close to that of zeolites, and thus a potentially valuable product from ash for water purification and for general catalysis needs. The issue is the cost of the fusion step and perhaps the rising value of ash that is now in more demand elsewhere. There are other uses and much more detail in the applications of fly ash in the full report, which is currently out for comment and will be available soon. Thank you, and thank you for your attention. I hope you've found the changing picture for fly ash to be of interest, and I will try and answer any questions you have.
Thank you, Ian. We have a couple questions here. Can you comment on the status of fly ash production and the use in the USA?
Thank you, Rebecca. Well, what's happening in the USA is first of all, the production of fresh fly ash is falling rapidly. We've already seen a large reduction in the coal power sector in the United States, and a further 25 gigawatts will be withdrawn over the next few years, which makes around a million tons of fly ash. At the same time, though, some states are requiring the removal of ash storage impoundments that are considered to be at risk of contaminating the local regions, and so that ash may be beneficiated. So that is a new supply of ash, and there is a vast amount of ash stored, but of course there is a cost involved in upgrading the ash.
Okay, thank you. What makes fly ash a better proppant material for shale gas recovery?
The reason is I mentioned about the increased lubricity of concrete when fly ash is added, and that effect it translates to fracking as well. And in addition, the wide range of small particles can penetrate further into the microcracks formed during fracking, and those particles resist compaction, so keep the structure open to release the gas. Right. Oh, now so I've got a few questions here. Let's see. Yeah, first question. You mentioned that fly ash to be used as a construction material should not contain more than 5 weight% of carbon, and ideally less than 2%. How does mercury control by activated carbon injection upstream of the ASB affect fly ash usage? It can increase carbon content, and it can increase mercury present in the fly ash as well. So in those cases, you would perhaps select the fly ash from part of your ASB array, and not the stage where you're looking for mercury absorption. But it would affect. In fact, it's important more for storage perhaps than the use of ash, except for the carbon content, which really does have to be low. The next question is, how do you see variations in coal quality in different parts of the world influencing the global trade of ash as a commodity? As the ash content rises, then the production of ash will increase, and that would potentially increase the supply of ash. But the main trend that's taking place is the transfer of coal use from America and Europe towards Asia, and that's creating a deficit in fresh ash production, regardless of the coal quality. Next question I've got is, considering the coal phase out in many countries of Europe, do you see a possibility of importing from third countries? The UK example is interesting. We're importing around 3 million tons of fly ash at the moment. Half of that's for concrete and half for aerated concrete bricks. And that example is going to hold for other countries. Germany currently has 84 coal power stations, which they plan to take out of service, and will need to import fly ash, especially as a country with a long history in the use of fly ash already. I understand that Poland are introducing export facilities in readiness to export more fly ash. Any comments on the impact of co-firing on ash quality, especially at high shares of biomass? For example, fuel conversions. I think I'll have to pass on that, but you have to be very careful on some of the salts present in biomass and how that affects how that will affect the quality. I think chloride might be an issue, because certainly it's something to be avoided in fly ash use. Have you thought about doing a study on bottom ash, and if not, is there any specific reason? But I haven't thought about looking at that specifically, but bottom ash, the composition is very similar to fly ash, and you can actually ground bottom ash very finely for its use. In the bridge I showed between Macau and Hong Kong, it was about 50-50 fly ash and bottom ash used there, and the reason they selected that was based on testing on models to provide the right strength parameters. Can you identify successes of recovering and beneficiating fly ash from landfills or impoundments? Yes, there's some key developments on that. There tends to be a thermal oxidation treatment to adjust the carbon content of the ash, obviously dried out. It may need grinding. It does have to remove mercury and ammonia, but that is already in practice in the United States. Let's see. Oh my God. Where can we find economical values of the different applications as far as they are industrial? Yeah, most of the new applications are probably just at the commercial stage. So there are studies, especially on the manufacture of zeolites, looking at the cost of preparation from fly ash compared to normal raw materials. But for things like carbon fiber and graphene, then people are watching the cost of production of those very carefully. as they could have a major impact on the construction industry. There's more questions on recuperating of existing deposits, but I haven't really covered that in the report. It's a different topic. I think probably we'll have to draw to a close there, as it's moving more into the questions I'm receiving are more about beneficiation of fly ash, which is really a separate topic. There are about 10 different technologies out there for upgrading fly ash, and perhaps we'll say more about that in the future. Okay, I'm going to pass back to Rebecca now. Hold on.
Thank you, Ian. The slides from this webinar are available to download from the webinar page of our website. You can also find our previous webinars along with this webinar on our YouTube channel. The next webinar from us will be on the 18th of March at 12 p.m. on co-firing biomass with coal, and will be presented by Xing Zhang. Thank you all for joining us today, and goodbye.